symplectic for manifold. Okay. So I start with introduction, let us say, motivating examples. First one will be example 1, this main, and this is result of Borman-Li-Wu, and it was about 2000 published 2014. So I say that recent result says for her recent is 2 or 3 years. So the different is ages. For me, okay. 10 and 20 years is still recent. Okay. Yeah, okay, good, okay. So example is like this. Exist 4-dimensional symplectic manifolds. So actually, it will be CP2 blown up in 9 points. Exist. Okay, omega. Yeah, have we exists P0 and P2 in X. Lagrangian embedding of RP2. So later I will say simply plane, because real projective plane, okay, it's too long. Okay, plane, and exists E0 and as this symplectic exceptional sphere. Exceptional sphere, and it means that self-intersection is -1. And this word exceptional means similar like algebraic geometry complex can be contracted. Okay, we have such a property. Okay, such that. Okay. Can be contracted. So we have symplectic sphere and symplectic for manifold. We can make what is called symplectic contraction, symplectic blow down, which okay. So term contracted comes from algebraic geometry. We mentioned this as a contract this rational curve to a point. Okay. Such that. Okay. The first property is simple. That P0 and E are disjoint. And if we contract, we obtain RP2 symplectic in this, in blow down, in this manifold downstairs. Okay, so we obtain, so to say, can simplify our situation like this. This is for pi 0. And for the other, okay, we have the following property. For any smooth, so it's conditional a little bit more, not symplectic, not Hamiltonian, but very smooth isotopy line of E minimal number of transversal intersection points is, so I write more or less true, okay, formally contradicting with word minima, okay, but okay, so understand is clear. So therefore I have this, put this intersect, sorry, I have forgotten, points of this deformation E prime and P2 is this two. So we cannot, how to say, displace, there is some another property, displace E from P2. We cannot deform E such that it will not intersect P2. This will always have intersections. And transversal intersection will be always 2. And second property is that P0 and P2 have the same homology class. So main goal of my talk is, so to say, generalize to explain this result, what's going on, why it is, and show how to construct. Actually, I give a almost in a certain sense classification of Lagrangian embeddings of planes of RP2 in symplectic for manifolds. So it will be full for rational rules, and for other will be some. Okay, we will see what I can do. Okay, and so to say, it's this one second example is okay. It's rather as a motivation. I call it Tori claims exist in CP2 with standard symplectic form, and by theorem of Tubbs, we know that there are only one such form. Yeah, okay, up to diffeomorphism. There exist Lagrangian tori. I will write this T I J K. I J K is I'm sorry, this Markov triple. There is certain natural numbers, starting with 1, which solve certain Diophantine equation. It doesn't matter. Claim is that for every such triple, we can construct certain Lagrangian tori such that the first property is tori are smoothly isotopic. Yeah, compare with previous question. Okay, it's even more than not quasi, but of course it is Lagrangian isotopy. But okay, let us drop for a moment these technical details. Second is they have the same period. And this periods means the following. We have certain bases, I call it D1, D2, D3. This is basis of relative homology class X and T. Okay, we know they're smoothly isotopic, that there is this group well defined. And if we take will be basis. And condition that integral of this over those disks, dj of omega is y. In the basis, this can be realized as disks with boundary D on such torus. Okay. On such torus, so HKL we have now 4 indices, 1, 2, 3 for the homology class, and IJK depending on what the torus is. Yeah. Okay. And the claim is integral of dj of omega is 1, so independent of torus. So this condition is also equal to this case is called the torus are monotonic. Okay. And main property about those the torus IJK are pairwise not Hamiltonian isotopic. It's not Hamiltonian isotopic. Okay. So these torus are from, to say, Lagrangian Hamiltonian point of view, they are all different.
So you mean that the non-driven element in the homology class, right?
Where?
Yeah, only the thing cannot be two is a non-driven cycle.
No, here it's not in sense of homology class, but to say geometric intersection. I consider deformation E of n isotopy, yeah? And try to minimize intersection points. I can always make it all intersection transversal. The number of modulo 2 is fixed, okay? Is the 2 intersection number will be so even or odd, okay? But we can make different intersection points, yeah? So for example, if we have, this is P, and if it is E, so you can always produce additional intersection points. Okay? Producing here. Okay. A question is whether we can minimize, how we can minimize those, right? And question is for first embedding, we can make 0, so it's already made 0. So it's adjoint, and for P2, we cannot do it. No matter what, how we deform smoothly, make which must smoothly isotopy, which means basically we can make deformation of both of this and this one. Okay, we never cannot remove this intersection points. Okay. Okay. So this is came with these two embeddings are topologically very different. And these examples which say that there are very many examples which are topologically equal, so isotopic, Lagrangian theory, but not Hamiltonian isotopy. So this finite invariance, which is, so to say, basically correct equivalence relation for Lagrangian manifold, then they are different. I do not discuss how it is proved, right? I just a statement. Okay. Okay, for my example, main examples, this I will add because of the results of the talk. Yeah? Okay. So I organize my talk a little bit other. So first I present theorems, and later I will build technical how I will prove this. Because so for my experience is rather negative if I start with explanation. So we lost in details, and then we, in the end, writing very quickly, trying to understand the main result is okay. Therefore, I do it in theorem 1 will be like this. This will be related to this theorem 2. We have symplectic moment for manifold. Right like this. P in X Lagrangian torus. Any, doesn't matter, okay. And E in X symplectic exceptional sphere. Exceptional sphere, it means the same self-intersection is -1, and or another one we can contract it. Claim. Exist stronger symplectic isotopy E prime of P, which is disjoint. Disjoint, and of course the immediately corollary E prime can be contracted. Okay. So if we compare this result of Borman-Li-Wu for RP2, the tori, the situation is rather opposite. Okay. And here we have very many different Lagrangian different, so to say, situation is one could expect. So for some is we have one possibility. Okay, now it's like this. Okay, the first reason is it's a for this theorem to compare this result with Borman-Li-Wu, and second, that the technique which I proved this theorem, that next result is what is called symplectic next stretching techniques, which I explained a little bit. Okay. Later.
Symplectic but Hamiltonian. Can you make it Hamiltonian?
This
Do expect it.
because you see you make a deformation. We have no one cohomology class and trivial. First cohomology of spheres is trivial, so this can be made as a Hamiltonian. Okay. But actually, the construction will be, as we see in proof, we make just more or less explicit. Okay, not explicit, rather implicit deformation, but construction will give us that during next stretching, this exceptional sphere must go away from the torus. Okay? And next there will be several theorems, and always will be applying of techniques of symplectic next stretching to RP2, and I just formulate the results. Theorem 2 will be that. So we have X for omega symplectic P in X Lagrangian RP2. So Lagrangian embedding of real projective plane and E in X exceptional sphere. Then one can, okay, I can define, one can define a number I will denote it N and E of E. More precisely, it depends on isotopic class of E, or because we have exceptional sphere and the properties is sufficiently to know homology class of exceptional sphere, because okay, there is good theory of pseudo-homologic curves which works very good in this situation, such that topological definition. MPV is a minimal number of intersection points of P and isotopy prime. Let me add. Most isotopic. So here we discussed Lagrangian, torus, and Hamiltonian isotopy. This is even rougher result. This is like in this theorem. Smooth and smooth isotopies. Transversal to P. Okay. So I try all possible isotopies of my original here. Okay, make it transversal to P and consider how many, which is minimal number of intersection points I get. So if I take, so expected, it's either 0 with intersection number is 0 modulo 2 or 1 if it is intersection is 1. Can we get this minimum? Okay. It appears that it's not always 1, but one can always introduce this number. Okay. Okay. Second one claim is the following. So to say, if equals 2, then exists a prime symplectically isotopic E disjoint and again can be contracted. So this, sorry, is m equals 0. If we have 0, there we have the situation which was with P0 in this claim. Okay, okay. Next example. If m equals 1, then this symplectic disks, right, D1, D2, with boundary on our plane. So let's go symplectic disk attached to this Lagrangian surface, such that symplectic, I have said, embedded. Such that Maslov index is yeah, of course. Disk in, okay, like in complex analysis or topology. Yes, okay. Dimension is 2. Maslov cos of each disk is 1. Yeah, okay. So it's, and this disk, so it's our, this exceptional sphere, so to say, splits in these two disks. Okay, this N H2 XP Z. Okay, so typical example is like this. We have, say, standard CP2, so to say, model example. Yeah, okay. Okay, good. Model example will be like this. So X will be CP2 and blown up in 3 points. Okay, and we do like this. If we make blow up in 2 points, there exists, make it all holomorphically. Yeah? Okay. There exists a complex line, yeah, which passing these 2 points and proper pre-image this will be minus one sphere. Maybe, okay, this. Yeah, okay. And then we make another one blow up. And we transform this -2 sphere into RP2. For this, we do it like this. So first of all, if we make two blow-ups, this line, this will obtain symplectic sphere, but it can be made, deform a symplectic form, it can be made Lagrangian. Okay? So the situation will be something like, for after two blow-ups, this will be a situation like we have a Lagrangian sphere in some symplectic manifold. Okay, and then if we made another one blow up, we made it, so to say, like in real algebraic geometry. The complexes are real. This will be give a blow up in sense of algebraic geometry here, and we obtain RP2 from this sphere. Okay, and as a blow up, we obtain here this Möbius strip, and with a line here, and along this Möbius strip, we have attached these two disks. Altogether, this will be last blow up. Okay, so this construction can be, this example can be constructed rather good, understood in sense of real algebra, real complex algebraic geometry. Okay. So it's easy to produce this one example. Okay, and second is, okay, if is at least two, okay, then exist if you write D0 similar to this one, symplectic disk with boundary lying on P. There exists a surface, symplectic surface, I will write it E because to say it's part of this E which was Biffinium. It's okay. Different letter, but okay, different version of this letter. Okay, surface, which is look like this, is a sphere minus m disks. Okay, and we can imagine it's like this. The boundary of this surface consists of m disks. Okay, and such that our class E will be m times D0 plus this E. Again, in this relative homology class. So here, picture of the splitting was like this. Okay, to this D1, D2. Okay, so if we take the same description and put m equals 1, this E will be sphere with one hole will be disk, and these two pieces are undistinguished. We cannot prefer say which is D1, which is D2. If m is higher, so we have disk, okay, and other component which is not disk. Therefore, it appears asymmetry. Okay, this is how it splits. Okay, so once again, so we have P Lagrangian embedding between some symplectic manifold, and we know the exceptional sphere E. Okay, then we look for minimal number of geometric transversal intersection points. Count it not with multiplicity plus maybe not with sign, but just the number of them. Okay, so okay, either there are no, they're disjoint. Okay, either we have situation, and this situation is basically typically so. I had constructed here this example as blow up of Lagrangian sphere, and one can show actually that this construction can be reversed. So have in such situation, I can deform original sphere in such a way that it will be looks like this, and I can contract this and obtain Lagrangian sphere on this manifold downstairs, which obtained. Or there will be a situation like this. Okay, and remark remark in Borman-Li-Wu example, m equals 2. It's how it is good is more complicated. No. Okay. No. Okay, let me say like this. So if I apply symplectic neck stretching to the construction, I have degenerations, which degeneration was exactly the splitting. Okay, and this splitting is, so to say, topologically unique because definition of M is topological. Okay. No, I cannot. Yes.
In order to basically place it in all those places where the boundary of E lives, you use
yes, this will be like this. So we can do, yeah, but you're right. So you can imagine the picture is like this is our P. These are copies of D which are isotopic. Right? So we have this copies because we can then deform N. Okay. This is D0 first, D0 second, and D0. Okay. We have here disks, and E comes something like this. Actually, the picture will be more complicated, but for a detail, okay, this is information. Okay. Okay. Don't let you. I see. Okay. So I will write and then push up. Okay. 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 And I will not. Okay. Maybe I'd later formulate the the higher results which can obtain. Maybe I add. Okay. This was theorem 2. Theorem 3. I did still technical. Like theorem 2. We have x omega p, and we have now two E1, E2, two symplectic exceptional sphere. Okay, so it's the same, but we have no copies, such that E1 0. Okay, and this is equivalent symplectic isotopy can make it disjoint. Okay. Okay. Assume that MP for E1 is at least one E of E2 at least one. Okay. So we can produce at least one disk. For M equal 1, this will be 2 disks and single disk with 1. Okay. Claim. Then, okay, the one of the disks for E1 coincides okay, I write weaker version, but it's more or less equivalent. Symplectically isotopic, relative relative is a condition that D boundary lie on D. So we make symplectic deformation such that boundary moves on P. Okay, coincides with the one or one of for sphere. Okay. So technically it will be like this. So I will make max stretching and make this conduction simultaneously for spheres which appears pseudo-holomorphic for E1 in the class E1 is the same for E2. And when it takes a limit, my curves will be made breaks in the pieces, and these pieces will be exactly what was he stated. The first and the second theorem that this either one of these two disks coincide with, depending we have 1 or m is equal 1 or higher. Yeah? Okay. If all are if all are both M1 and M2 is at least 2, then I have single disk in for first class, single is for second, and they will be the same. Okay. Okay. And okay, using these two technical results and some other which are okay, it's even more technical to formulate in the front of you. I formulate like theorem 4, generalization for of Borman-Li-Wu exam. That n, okay, let me at least 1 be fixed. Okay. Okay. Then on x, I will write x10. This will be CP2 blown up in 10 points. Okay. I recall geometric basis is L okay. So I use the same paper for line. So the holomorphic or pseudo-holomorphic theorem is the class, the generator of homology of CP2 or the homology class of CP line, complex line in CP2, and this homology class of exceptional spheres which obtain. Okay. Okay. Just remember this. There exists a symplectic form depending on n, one can choose. I cannot choose the same for all arbitrary n. So what will give this will be some interval from 0 to or for 0 for n, and symplectically this result can realize for finite range, but not infinite range. Okay, the symplectic form, and there exists Lagrangian embedding so we have fixed manifold Lagrangian, the form is the same, okay, and but embedded such that, can I write still here? It's okay. Yeah. Okay. Okay. The table of J values is okay. So I compute this number, can compute for each Lagrangian embedding of P, and for which exceptional class. Okay, so this is the whole table. And a remark, I can do it also for class L. This means the following. I consider pseudo-holomorphic spheres or symplectic spheres passing through two fixed points. It behavior like the same like exceptional sphere. So number is defined in the same way. There's no difference. And table is like this. This. Let's remove K. For this, classes will be number and value will be the same. Sorry, let me. This is wait. I have now this one. So I start from P1. And E9 and E10. The forward set. Number M, this minimal intersection number of this PK with L will be 3K. Here will be K plus 1. Here will always K. Here will be K minus 1. And here will be 1. Okay? So for example, here will be 3, 2, 1, 0, 1. Okay? Lagrangian embeddings of RP2. And if we take these numbers, which say this in table, modulo 2, this will give us a homology class of this RP2. This will be homology class. Okay. So it implies that P the same and P odd the same. So depending on parity of this K, they will, if the parity is the same, they will have the same homology class. Okay. So, okay. And because the number of M is different, they are not even smoothly isotopic to each other. Isotopic. So you can show it like this. So this number M, this will be equal to the number, in most cases, this will be equal number. And here for line, we have, okay. Okay, so this is what I claim to be proved. Okay, what I claim is possible to prove. Okay. So I do not need make a copy a picture of this, yeah, okay, because it's registered all this. Okay, good. So as I said, it's almost end of the talk. So I just want to sketch explain what is going on, what is good. Okay. Ah, okay, this one. You have this device. I was starting to telling this story. There was once Anosov was visiting and making talk in Bochum, and they have similar system, but we do it larger in 3 tables, and use all the 3 tables, and then also start to laughing what he will do with the device. There was 2 separated devices, and he put them together. So it's just, okay, and first one, Nas vision, wish it, okay, and this one make it dry, and so in 3 seconds it was all people were very impressed. I don't know, but okay. So I'm not allowed to give out names or different phenomena. Okay, doesn't mean, but what's really so techniques. So I write the word. So we was discussing what use of artificial intelligence. I use this one to make translation of the word neck stretching to, how does this, medical type Greek. So Greek, which I use in names of diseases or something like this, okay. Okay, so this Latin word will be, this is Greek and Latin will be extendipolis. Yeah, okay, extended, okay. Okay, I don't know, but I'm not so good, but okay, okay. So this is not a name, okay, and because if you consider what analysis and geometry of symplectic, what is this? Analysis, geometry, topology, symplectic, or was a Greek, so it's okay to use even more Greeks. So techniques is what is called symplectic neck stretching. And I think the rough idea is like this. So first of all, what we have is like this. This is very special. L and X omega Lagrangian. Yes. Then this is a theorem called was Darboux, Weinstein, Moser, Weinstein. Exist U of L symplectomorphic to U prime in cotangent bundle. Okay. Then the following result that boundary of such U is of contact type. Is of contact type, and this means that omega is written like d of et times alpha. I will call this one Y. Alpha is contact form on this Y. Okay. And the picture is like this. So here will with pieces E minus, which is actually our neighborhood of our Lagrangian submanifold. X plus in our case will be with a complement to this. And here we have piece which is Z, which is cross Y cross interval A B interval. Trick is replace omega, which is symplectic, in Z by so if we take this presentation and multiply it by Z, we obtain a new form. This is not symplectic, but translation invariant. And we additionally, we construct J, new one. Okay, here will be J, this is the usual in X plus minus. And special, do not want to go details. Again, translation invariant. In Z. Okay. And after this, I can make stretching because on this part, okay, the object which I have, show this on the tilde, okay. Omega tilde, okay. This is invariant and J is special with also invariant. Okay. Then what will appear is that our manifold will look like this. This pieces remains geometrically the same, or nothing changes, and this will be cylinder will be this contact manifold Y cross 0 T, and T goes to infinity. And this is neck, and this is stretching. Okay, so this is construction. And and after this, we can do the following. Describe limit of JTN holomorphic curves Cn as Tn goes to infinity. So say fixed homology class C. Okay. In our case, this class of Cn is class E for each T exists and unique curve E J T in this class and JT holomorphic. So once we obtain the sequence, okay, I forgot the details of something like certain genericity conditions should be met, okay? So I can take this one, okay? And the situation will be claim. And similar, if we claim the class for line, we must additionally put condition that this curve goes through two fixed points, okay? And the claim, we can describe limit. Okay, described. Is P. It's very good. I can describe the limit claim. Limit will be a little bit more complicated, but the pieces, the curve brace which lives here, are exactly which appears in this theorem. And because of uniqueness, I obtained this what was claimed in theorem 3. So this disk must be 1. So it's rather easy notation. And in theorem 1, torus. So claim is that there will be no breaks, and this means that after some time, as we make Shevchishin long, the curve which which live here. More accurately, it goes maybe a little bit here in this cylinder, but only fixed on the fixed depth. So it does not go infinitely in this direction. It depends, so to say, and finally compact type here. Okay, so this is the claim about in the torus theorem. And explanation is why. If there is a break, so if yes, then one of component will be the following one. This will lie in X plus. This component will be a disk. Mu of this disk must be 2 because torus is oriented, and this means that Maslov classes in my normalization must be even, okay? And the condition is that limit of this disk will be on a torus. This is y. And this will be some curve gamma on the torus. This curve will be very close to a geodesic with respect to some flat metric. Okay, so as a contact form, I use first the contact form which comes from constructed like in Riemannian geometry. So you have this property that Hamiltonian geodesic flow on Riemannian manifold is Hamiltonian flow with respect to the function norm square, 1/2 norm square, and another description, this is rep flow of the unit sphere bundles over this Riemannian manifolds. Okay, so I know this all the possible these limits which hang, and key idea is if I for E from the sphere, expected dimension on deformation thanks of pseudo-holomorphic curves is 0. They are rigid. In the limit, we still get rigidity. Mu equals 2 if we compute the disk with mu class, Maslov class mu equals 2. The topological expected dimension, topological index of the problem will be 1. Then it could be formed persins, or it's contradictory. Then appears that the geometric index, which appears as real, should change from this, which we compute using index theory from topological situation by subtracting Conley-Zander index of the certain construction. This means this dimension 1 will be transferred for the next components, which lies not X plus. And then I can show why it is also a contradiction. Therefore, we obtain the contradiction curve cannot braid, and there is this result that E somewhere will disjoint from K. Okay, thank you for attention, and sorry for. Okay. Okay.
For is
Yeah.
say that even with the fixed symplectic form manifold that you below a CP2 by 10 points, and you can how to say, invent a lot of the complicated different embedding.
Yeah.
So that is the mean that do we have some way that you just try to on to think that can you use some information here to that is we don't have the hope to use this Lagrangian embedding to distinguish symplectic manifold.
Okay, so I reformulate maybe your question is like this. So question is how we can embed what are possible configurations, example of embedding of RP2, Lagrangian embedding of RP2 in symplectic manifolds.
For example, in G2 geometry, they try to count the associative submanifold as consider that is a invariant. So that's for example, but I think that if we fix some homology class, then I try to consider the on the Lagrangian embedding RP2 and divide it now by symplectic isotopic. But there is no way to how to say to make some new invariant from
New invariant of what?
symplectic manifold.
Yeah, okay. This was my reformulation. So what we configuration we have?
Yeah,
If you, for example, impose additional conditions, so we have fixed some properties of symplectic manifold or class, or maybe we have fixed symplectic manifold or something, okay? Then we can impose, for example, condition, is really some examples. How much different embeddings we could have depending on cohomology class of a symplectic form. So you can, for example, condition here, what is what? The condition was here, this dependent, yeah, okay, each form. The more complicated, the higher M we get. So if we have more example, this form should be very special.
Yeah.
Okay, this will be, okay. Yeah, okay.
Yes, so that's
Okay,
only a-
so this symplectic forms looks like this. Here we have 9 classes, and we hear this number M is almost the same. You can imagine something like this, that we take a 9-point blow up of CP2. We know that the Chern class is 0, okay, but it's still something saying partly resembles this Del Pezzo result. So we deform a little bit omega from cohomology class C2 to a little bit where it is square is positive. Okay, and the more here we have, the smaller this deformation should be. And this one class is also should be very, very, so blow up the volume of this form should be very small. So here the volumes of these classes is more or less 1, okay? So the whole is a little bit less than 1. Here's very small, and altogether it still will be symplectic, but sufficiently to produce this as example. Okay, this is a point. Another, okay.
I forgot that you write the different omega energy. Yeah.
Yes, okay. What do you mean?
Because
This omega,
yeah, omega n.
so omega, this will be like this. We take on this blow, here is 10 blow-ups, okay? I take 9 blow-ups, it takes the corresponding Chern class. This will be 3L minus all these classes, okay, yes? Okay, this form will be, so to say, degenerate square is 0.
Yes.
Then I deform a little bit, diminishing the periods of this one, so that will be a positive intersection. Then make this additional blood also very small. This is symplectic. In a claim, I have certain computation with, okay, explain, which shows how to produce this example. Okay.
So that's the same way can we do for inside a sphere, but sphere simpler. So you want to play something more complicated. You need the next stretching process.
No, sphere is so sphere is why it is so. Basically, yes. But the key idea is so that if you have Lagrangian minus 2 sphere, you can deform you a little bit, make it symplectic. Yeah, okay. And then you can make symplectic in one orientation, in opposite orientation. Okay. And then you to say you can apply this Gromov theory for both of them, and you get like this. So for example, if we have rational ruled manifold symplectic, okay, then we can describe what kind of -2 spheres, for example, we can obtain Lagrangian. Okay, for example, irrational ruled, which I take pseudo-holomorphic ruling with exceptional fibers, and one can show that if it's irrational rule, this -2 sphere will be necessary component of a singular fiber. And this gives me, so to say, question what homology classes is, how many isotopic classes of this first symplectic sphere are produced, and then it gets transferred to Lagrangian. Okay, actually, this here is also picture because the so-called constructor is called rational blow up, which transforms is Lagrangian RP2 in symplectic -4 spheres. And from this, so to say, from Hamiltonian point of view, this construction is very similar if we deform Lagrangian sphere in symplectic sphere. It's okay. In coordinates, if we consider the dynamics of this and that symplectic manifold, it will be very similar.
I have one, so I think in this work of Borman-Li-Wu, they also play, I mean, they don't just analyze this, whatever, bold Pekin or Pekin problem, but they also show some flavor theoretic properties of these Lagrangians, in particular things like superheaviness and other stuff. Things like superheaviness, superheaviness in quantum homology, and yeah. So my question is like, they do it only for the situation when the number of blobs is up to 8, right? So they perform only up to 8 blobs. Here you do it for 10. Like, do you expect, I don't know, do you expect any interesting properties for this? Yeah. RP2.
This will partially, okay, extension to the answer of your question, and probably, okay. This way, we'll erase this one. Okay. What does it mean? I don't know. What does it mean? Super heavy. Okay. Yes. I see. Okay. I understand what you mean. So it's like result what could be geometric what geometric configuration from point of view, not in homology, but really in geometrically, yes, geometrical, topological, set theoretical topological. Yeah? When you do, you apply different type of isotopy, smooth, symplectic, Hamiltonian, okay? And how much we can or cannot displace, move one from another, something like this, okay? Okay, and the answer for this result is mostly like this. So assume we can do that, yeah? Then we obtain configuration, certain configuration, and we can say something about certain configuration. So we reduce this question to the question of actually of Gromov-Witten invariance. Yes, because invariant, which I defined here, is not homological. This definition of M is not homological. But I will give you construction, which partially from for your part, which was the following. Recall that I have this P, I have neighborhood of this tubular neighborhood RP2, and I know that is S3 modular group Z4. Okay, and I have noted that rib flow of alpha contact form, I write it round. Then I take a round metric on RP2, consider rib flow of this. Okay, is integrable And we obtain some projective. As a symplectic reduction, we obtain sphere with a standard metric between, okay? And this bundle is the, how you call this pre-quantization bundle, what you call this principal bundle, C1 of L line bundle, yeah, okay, is depending how we define orientation, it will be +4. It can be minus or +4. No, sorry, -4. And this means that we can replace U of P, this boundary U P. This will be the same as boundary U of sigma -4 spheres. They're equal. And what we can do, we can make the direction blow up, yes, cutting this piece or gluing this piece, and this will be symplectically. Okay. And the claim is that what we have here in this table, so we get the following one. So this one can be transferred there as a every of this kind, it's not exactly like this, but it's transfers. But intersection number, this will be exceptional spheres, and intersection number will be this exactly this number M, which appears there. So on, okay? And additionally to this one, we produced another one sphere. I call this E0. This is exactly from this disk one, or like in this other is the theorem, this common disk is will be this one disk. We use a sphere, okay? And claim like this: periods of omega here can be computed by periods of omega, but this situation is very clear to describe. We can describe it because the theory of Li-Wu shows how to describe this situation -4 spheres. You can describe it like this. And in the special case where the blow up is too small, so up to 8 blow up, we cannot construct this example like this. And for example, if we put P equal 1 or K equal 1, okay, this K minus 1 will be 0, and this can be eliminated. This sphere we get 9 points. So in 9 blow-ups, we get only one example, and this is example for Borman-Li-Wu, and there are no more complicated. And to get more, we need at least 10 blow-ups, but then we can arbitrary range obtain. Okay, and I think that what they formulate is more or less related can be described or can be managed, treated using this approach.